Yeah, hi everyone. So I put together this LLMs in Python talk, and there are a couple of things I want to discuss today. So first, I want to define what it means when we are saying we are running LLMs in Python or we are training LLMs in Python. Second, and I think that's going to be the biggest part, I want to talk about what we can learn from coding LLMs in Python, like understanding LLM architectures. What are the patterns, let's say, are revealed when we are doing the hard work and implement LLM architectures in Python, look at the code differences and so forth. And then third and fourth, I want to talk a little bit about the trends in AI, what's next, what are the current LLM architecture trends and so forth, and also give you some getting started tips in terms of what are some of the projects as a roadmap that you could maybe take a look at if you were to get started, like from a beginner level in understanding LLMs to more like intermediate and expert levels, like just like an overview of things that I think are useful, like open source projects and so forth. And so with that, getting started. So the main, or the first thing I wanted to show you is this small but hopefully motivating example. So this is an LLM that is running on my laptop, just a very small LLM, and you can see it's pretty fast. So I have to admit, okay, this is a pre-recorded, but I didn't speed up the video. It's a LLM that is running locally. And here, the LLM itself is coded in pure Python, so 100% Python / PyTorch. So this is actually using PyTorch, but GitHub shows it as 100% Python. So this is, it's like a very, very small LLM, but very, very capable given its size. And the interface is based on Python and TypeScript. So TypeScript is a language it's like a JavaScript library. So to make it more, let's say, easy to use, but here I'm using Chainlit. So Chainlit is an open source project that you can use to implement ChatGPT-like interface if you have arbitrary Python LLM implementation. So this is actually an LLM from my build a reasoning model from scratch repository, locally running and in pure Python and PyTorch. So I mentioned earlier I wanted to briefly define what it means when we say we are running LLMs in Python or using Python code. So here, like I already mentioned a couple of times in this very short beginning, is that when we use LLMs in Python, it's not literally pure Python. It's usually through the PyTorch library. There are different libraries. There's also JAX and MLX, but PyTorch is by far the most popular library for LLMs or AI or machine learning, deep learning models and so forth. And under the hood, PyTorch is using C++, for example, if we are running code on the CPU. So when we are typing something out in Python, it goes through the PyTorch API, the PyTorch Python API, and it calls then some here in this case, C++ code if we are using the CPU, just to make it faster. So in that sense, PyTorch is more like the glue between Python and fast C++ implementations. If we have a GPU, for example, CUDA or NVIDIA or AMD GPUs, it uses either CUDA or ROCm. So we just type CUDA, it's for ROCm, it's also CUDA. It might be a bit confusing, but that's what it is. So in this case, it would run in the CUDA language, which is essentially a flavor of C++, and then or if we have AMD GPUs, ROCm. And similarly, if we are using MPS, it would use Apple's Metal backend, which is a way to use the Apple GPU in the Apple Silicon chips. Long story short, just defining what it means when we are saying Python code. So it technically means PyTorch. But I think most of you probably already know this. It's nothing like really new. People have been using PyTorch since, I would say, 2016, 17, a long time. And so you probably already are familiar with that. Just a quick overview of the LLM ecosystem and tools that exist. So I already mentioned Python and PyTorch and JAX. So for training, most tools are based on these. So it's usually for experimentation Python, like implementing the idea in Python PyTorch, and then under the hood, that one uses CUDA. At some point, if you are training very expensive models, you want to optimize things, because if you are training a model for $50 million, if you get a 10% speed up, that's $5 million that you save. So it might make sense to optimize it. So often people write optimized CUDA kernels. There's also basic torch.compile that also already does some of the heavy lifting, for example. Some people also export it to pure CUDA, but usually, based on what I know, is most people I know would still start with PyTorch, because it's just faster to iterate. And once you have something where you're happy with, let's say, the training loss in the first iterations, you are happy with the code implementation and so forth, you can always switch to a, let's say, more pure or optimized CUDA version of your code, basically. Then usually after training, we have this whole ecosystem around Hugging Face Model Hub. So the Hugging Face Model Hub is essentially like GitHub for LLMs. So here, most people share their open weight implementations, and they are also then compatible with the Hugging Face transformer library. So that's like almost like a bottleneck. The whole ecosystem goes through the Model Hub. And then when we use tools in inference, for example, when we download open weight models and we want to run them on a server, we would, for example, use sglang or VLLM. Or if we just want to run something on a smaller device like a laptop or a desktop computer, often I would say Llama CPP or Llama are popular choices. MLX is the PyTorch equivalent for Apple, but Llama also has MLX support. So it's usually, like one of those that we would use when we run LLMs. And these are not Python-based, basically. They're more like, in this case, Llama CPP, CUDA and C++ based, and so forth. But yeah, so that's just like a quick overview over the ecosystem. But like I said, a lot of that starts with Python, goes through the Hugging Face Model Hub, and then later on there are the non-Python tools for serving LLMs. So for this talk, I want to mainly stay in the Python, let's say, ecosystem, and talk a little bit about what we can learn from coding LLM architectures in Python or PyTorch. And I think it's going to be quite interesting because there are things that we can learn that are not necessarily covered in blog posts or papers, because nowadays I think the dilemma is that papers are a bit less detailed than they used to be. I mean, because it's mostly open weight models or open weight LLMs, they mostly come from company labs rather than academic labs, and there is usually no, I guess, peer review in a classic sense with, conference submissions and so forth. So they're more like white papers sharing the overall idea. Mostly they contain the benchmarks, comparing the model to, let's say, other relevant models, but it's less often that a full, let's say, detailed coverage of the architecture is included. And so what we can do, though, is we can look at the code, because if people upload the open weights to the Hugging Face Model Hub, and we can load that into the Hugging Face Transformer library, we can actually read the code and see what's happening under the hood. And working code, like I'm mentioning here, working code doesn't lie. With that, I mean, if we have code and the code works and it produces, let's say, the correct results compared to a reference implementation, we know it's correct. So otherwise we would get different results. It's kind of like almost like a self-check, like in reinforcement learning with verifiable rewards. It's like the verification here. So if we compare our implementation against the reference implementation, and there's a lot we can learn from there. And so in the next couple of slides, I hope that is something that is interesting to you, because a lot of people asked me about that in the past when I showed my architecture, let's say, sketches and drawings, how I come up with them. And so I thought it might be, just fun to share my process, basically. So if you want, you can turn this into maybe a Claude skills.md and automate this. But this is like a purely manual process, because I think it's quite useful. It's like the learning process, because if you automate things, well, you also automate the learning, and then you kind of lose a bit of the understanding again. And so I think doing this by hand for not every architecture, but for a few of them, is actually a great way to understand how LLMs work. And so here I'm going to show you my personal process from config files and code on the Model Hub to some of the architecture insights and basically the figure here on the right. So usually it starts with the news. So I'm probably checking the news too often these days, but usually, well, new model releases are announced on one of the social media platforms. I'm picking here Gemma 3 because it's a small model. Gemma 4 just came out last week. I do also have implementation of Gemma 4, but it's a bit larger. So I thought, let's just pick something simple like Gemma 3 270 million because it runs on basically every computer. It's a very small model. So usually it starts with me discovering that there's a new model somewhere on social media, for example, or a blog post and so forth. And what I would do then is I would search for the technical reports. In this case, there is a Gemma 3 technical report on archive, and there's also a blog post. It's not always true. Most of the time there is a blog post. Often there is no, let's say, detailed technical report. But if it exists, I would definitely check that out because there is always, or not always, but there's often a motivation for certain design choices that are not necessarily in the code. It's in the code you see the end result, but sometimes in the technical report or the blog post there are some more, I guess, explanations sometimes why people did something a certain way. Anyways, I would read that first, and then I would go to the Model Hub page where you can find the model weights. Of course, the whole talk here is about open weight models. It's not about ChatGPT or Claude or Gemini because those don't have open weights, so it's impossible to really know how they look like under the hood. So this is for open weight models. So usually there is a Model Hub page. And on the Model Hub page, there's also sometimes or often a detailed README file with a lot of information. People call that often the model card. So the model card is essentially just a detailed overview of benchmarks, some code choices, and so forth. And then from the Model Hub, I would look first at the config file. So the config.json file is a file that specifies in a JSON format some settings that are then used by the Hugging Face Transformers library. It contains a nice level of detail. It's not overwhelming, but some of the detail is hidden inside the transformer code implementation. For example, here we can see it uses a GELU activation, hidden activation, GELU PyTorch 10H. That's like the approximated GELU function. Here we see it's using sliding window attention, 5 sliding window attention layers, and then 1 full attention layers. So we can get some idea of like how certain things are implemented. But other things, they are hidden in the Gemma 3 for causal LLM class, which is part of the Transformers language package. But again, there is already a lot of information right here. So what I would do with that information is I would take one of my previous figures, for example, starting at the very beginning, GPT-2 XL, or if I have a newer one, for example, Qwen 3 in this case, it's, I mean, not super related, but it's a bit closer to Gemma 3 than GPT-2. So I would look at one of the older ones where I already looked at the config files and would just, read through it, have them side by side and see what has changed and then just update the figure. So I would, for example, here I have the GELU activation. I changed it to, it's actually SWIGLU. It's a CELU activation with the 2 linear layers here, the gated layers and so forth. And then for Gemma 3, we just said it has, again, GELU activation. So I would change CELU to GELU, but it has actually a GEGLU. That is maybe not part of the config file, but you would see that in the Gemma 3 for causal code. Anyway, so I would make all the updates that I can in the figure based on what is here in the config file. It gets you so far, but it helps you to get like a general idea. So there are certain details. So for example, the norm placements, I think I either got that from Gemma 2, like instead of using Qwen 3 in this case. I have actually a blog post where I did that in the past. So, but this would be something that is not really evident in the config file. But then, yeah, I would go next to the code where you can then fill in these little little missing details. For example, here, taking in a related architecture, for example, I would just open my previous code where I coded up an architecture and see how I have to update this to get to, let's say, Gemma 3. So this would be from Quen 3 to Gemma 3. And like we said before, I would replace the silo function here with Gelu, for example. That would be one update. And I would go top to bottom through the code, make these updates based on the config file, seeing how far I get. And at some point in the code, there's also the weight loading part where the pre-trained weights are loaded into that architecture so that we can use that architecture. And so what I would do then is, once I've coded everything up, I would run a basic text generation. So I forgot to include the prompt here, but the prompt is something like, explain how an LLM works in 2 sentences or something like that. So I would run this code and I hope that it generates a coherent answer as text. In this case, so this is actually what really happened. So in this case, I get some gobbledygook. So Gemma 3 is a multilingual model. And yeah, it responds in a foreign language. The prompt was in English, and it responds with these tokens here, and I have no idea what it means. And what I can tell here is that it made a mistake at some point. So at some point, there's some implementation, some coding error, and it gives me back this text, like just some random tokens, basically. And so how do we fix that? So what I would do next is I would go through the architecture one by one. I would start at the bottom, starting with the embedding layer, and then the first transformer block here in the center, the first normalization layer, and so forth. And at each layer, at each position, I would compare this to a reference implementation. So the reference implementation would be, for example, the Hugging Face transformers library. And so at each step, I would compare the output at that layer. So I would just, automate this, write a script, and run it layer by layer. And here I would typically use random weights, just like a smaller model. So here, for example, you can see there are 18 transformer blocks, but I'm only running block 0 and block 1, so 2 blocks, just as a quick sanity check, so it doesn't take forever to load the model and so forth. And I can already see here there are a lot of differences. And starting at the top, so OK embedding. So that means that the embedding layer has no issues. It computes everything correctly compared to the reference implementation. But starting in the first block, looking at the input layer norm, it's the first pre-RMSNorm layer here, I already have a deviation. So I can see the values, the mean of this tensor there is off by 0.8, and the maximum value, the highest value in both, is off by 2.3. So it's quite a big, it's not a huge deviation, but it's quite a noticeable big deviation. And this deviation propagates then through the whole network. And that is why I get like nonsensical outputs. So the task here now is to find out, why is this not working? Why do I get these different results? So what I would do next is I would go into the transformers library and find where the code is for Gemma 3. So here there is a modular gemma3.py file, which has some of the code that is used to implement Gemma 3 in transformers, and then usually it turns into an Easter egg hunt, because the transformers library is quite complex. It has so many different LLMs, it has to support them all, and ideally it reuses code here and there. And it's more complicated to read than, let's say, simpler from scratch code. And that's also the whole point behind implementing things from scratch. It's that we have a linear, minimal implementation for learning purposes, rather than this super heavily abstracted, optimized, refactored transformers library. Not saying transformers is not great, but it's a different use case. It's less for learning, it's more for actually running things. So yeah, I would go on this Easter egg hunt here from modular Gemma 3, finding the Gemma 2 RMSNorm here, and then going to the file where Gemma 2 RMSNorm is implemented. In this case, it's just a pass, but I see it's inheriting the RMSNorm from Gemma 1, the first Gemma model, basically. So I would go to the file where that is implemented, and I found it here. And what I can see is there is something peculiar about the RMSNorm in Gemma. So for example, here, if you're familiar with RMSNorm, it looks a bit different. They have this, instead of multiplying just by the learnable parameter, they have a times 1.0 plus the weight. So it's a bit different from the usual one. And so that tells me, okay, well, that is probably where my problem lies, because I copied over the RMSNorm from a previous LLM into Gemma 3, and that's probably why it doesn't work. And I now have to adjust. And yeah, and so here I would then go back to my code, take the code I had before, and then adjust it to make sure it gives me the same results as the one in transformers. You can ideally also implement some unit test to double check, but yeah, usually, you know, I'm not super lazy, but I'm a little bit lazy, so I would just make the fix directly in my code and then run my checking tool again and see if it works. By the way, if you're curious, I already forwarded to that slide. What we can learn here is, so going back one more time, so I make the adjustment, and ideally I also want to make sure, well, I learned something from this experience, because that's the whole goal here. It's like implementing something from scratch is not to, it's not to sell it or to run it super efficiently or anything like that. It's really primarily to learn and to see, what do architectures look like? How are they different? What can I learn from this change here? Why did they do that, basically? And so in this case, the regular RMSNorm and the Gemma RMSNorm, they can give you the same results, but it's just like how they set it up can stabilize the training a little bit, or the training of the RMSNorm part at least. Because in the regular RMSNorm, we have a learnable parameter here, let's call it gamma. It starts with a value of 1. So usually you multiply the RMS times gamma. And then this is a learnable parameter that is learned during the training. And in the case of the Gemma RMSNorm, it gives you the same results at initialization, but they have this 1 plus s term. So in this case, they are setting s to 0, and then you have still this multiplicative factor, RMS times 1 plus s. So I should have maybe included the whole formula, but it's only a side note here. Basically what we can learn is that Gemma has the learnable parameter centered at 0, and that presumably makes the training more stable, because usually traditionally in deep learning, if we have 0-centered parameters, it's easier for something like Adam to optimize this compared to something that is offset from 0. That's the whole point here, basically. And so yeah, by doing this from scratch implementation, we can actually learn these little nuances. And now we learn something new. We learn something that, hey, there's a regular RMSNorm and there is this little more stable Gemma RMSNorm, and maybe we can adopt that for our own architecture in the future, for example. So and then I would run my checking tool. Here it's like a shorter version of that, where it shows me now everything after adjusting the RMSNorm looks okay compared to the reference implementation. So it means basically my implementation is more or less doing the same computation as the Hugging Face Transformers one. So it tells me, okay, now I understood the Gemma architecture. Now I have done, let's say, the hard work. I implemented it, it works. And then just as a sanity check, I would also run this with pre-trained weights. So just going back one more time, this is just, randomly initializing the model, making just sure both have the same initial random weights, and then running only 2 blocks instead of the whole 18 layers. Here, now we are implementing the whole model, loading the whole 18 layers, loading the pre-trained weights in that model, and also generate the text, for the prompt, basically letting it answer the prompt. In this case, the prompt again was something like, summarize how LLMs work in 2 sentences or something like that. And so yeah, it generates coherent text, which is a good indicator that our LLM works correctly, given that we also know that it produces the same outputs at each layer. But just to make sure, I would also do the same thing with the reference implementation, here using the model from Hugging Face, and then making sure both create the same text. If there are some differences, it could be, for example, that there are small rounding errors or so forth. But it's usually, if we do a good job and use, let's say, bfloat 16, it's usually almost always identical. And yeah, and this is like, I guess, my 12-step learning procedure for understanding how LLMs work if we have like a new model release, for example. I don't do this for every model. So for some models, I take more of a shortcut and just look at the config file, because the config file is already so self-explanatory that I don't really need to re-implement it. But if I had more time, I would definitely do it. And so yeah, here is like a gallery I made. There are more than 50 LLMs in this gallery now, and I wanted to just show you, if you're interested, how you can find it. So it's here at the bottom, llmgallery.com. So I made a short URL. This basically just points to my personal website where I have this gallery, and it has a whole lot of information about each architecture that I thought might be useful, like the links to the config file too, so you can just click on it instead of searching the model hub, for example, a tech report if it's available, all kinds of things. Also, there is a comparison feature, so you can compare two architectures with each other, see what is different between those two architectures and so forth. And yeah, hopefully that's useful. It's just like, like a little side project. For this talk, though, I wanted to take this side project and talk a little bit about what are the trends that we can observe from looking at these 50 architectures or 50 or more architectures. So what is something that is interesting, something that stands out here? And so most architectures, or if we look at the timeline of architectures, they're really focused on strategies for reducing the KV cache size. So, I mean, if you look at these architectures, they look mostly the same. I mean, it's all mostly transformer based. Some of the, attention transformers and attention based. There are some, we will get to that later, they have state space model layers, but most of them look almost identical. And there are little nuances, and these nuances that differ are either the sizes or like the attention implementation, and usually with the motivation behind it being the KV cache size. So why are we currently interested in reducing the KV cache? So the KV cache uses memory when we are running an LLM in inference, and we are nowadays needing longer and longer context. We need more input to the LLM because now we have reasoning models that output like intermediate results, and we have agentic harnesses which provide the LLM with additional information, for example, about the project we are working on in. For example, if we have, let's say, something like OpenAI Codex, and we run a query through that, it gets all the information from the GitHub repository, and that needs, of course, more memory because we have longer context, and longer context results in bigger KV caches. And so what is a KV cache? Unfortunately, we don't have that much time to go through this. It's a whole lecture by itself. But this is like a slice through the attention mechanism. There are computations, intermediate computations of queries, keys, and values. And these keys and values in different iterations, they are, when we generate one token at a time, they are going to be repeated. So instead of recomputing them, we store them in a KV cache, and then we retrieve them from a KV cache. And if we have a very long sequence, this KV cache grows essentially. If you're interested in more details in how this is implemented, I do have a coding from scratch blog post linked down here. But yeah, so the main idea here is that we are reusing keys and value computations throughout the generation process. But then this makes everything faster because we don't have to recompute them, but we have to store them. So the storage is basically the concern here. And so one idea or multiple ideas center around modifying the multi-head attention mechanism. So here, this is the classic GPT-2 architecture. We have classic masked multi-head attention here. And in multi-head attention, just like a sketch here, we have for each query a key and a value. So here what we are looking at is the multiple heads in multi-head attention. Unfortunately, again, I mean, this is not a lecture on attention. I do have a blog post I could link if you are interested, but just, for what we are concerned here is basically this keys and values that they accumulate storage space if we have a very long sequence. So it scales with a number of heads and also with a sequence length. And so one idea is so-called grouped query attention. And group query attention is not a new idea. It's like something, I think it came out in 2022, 2023. I think one of the Llama 2 models, I think the larger one already used that. So it's not like super new, but it's still very, very popular and very relevant. And the idea here is that for a group here, so we share the keys and values. So here we have so-called two shared KV groups. So two queries share the same key and value instead of having one key and value for each head, basically. And that reduces the KV cache size because now instead of 4, we have only 2. And so we reduce the KV cache size by half by just sharing. The downside is it can affect the quality of the responses a little bit. Usually it's not too bad if we choose a reasonable size, but it has, it is an approximation. There's some sharing going on. So it's kind of like a workaround, but it's usually worth it in practice. And so a lot of architectures nowadays still use group query attention. For example, Llama 3, Qwen 3, Zarvam, it's like a new model from India, like a big model. We will get back to this later. That's the reason why I specifically put it in here. Gemma 4, which just came out last week. So Gemma 4 is also using group query attention. Lots of architectures use group query attention. And here's like an overview just to illustrate the motivation behind it. So on the y-axis, we see the KV cache size across all the layers in a given architecture. And if we use regular multi-head attention in this particular setup, we would use 52 gigabytes of KV cache storage. So that's like a lot. I mean, if you think about how much RAM a GPU or a computer has, 50 gigabytes is a lot just for storing keys and values. And so if we use group query attention with 4 KV groups, we reduce that by a factor of about 4. So we have 4 times less KV cache pressure. And so also you can see maybe important point here is it scales with the context length. So the longer the context, the more expensive the KV cache storing becomes here. So you can see at 128,000 tokens, we go from 52 to 13 gigabytes if we use 4 KV groups. You can even use more groups, so you can go 8, 12, 24. It becomes cheaper, but again, it can also then at some point be too small, or there's too much sharing, and then the quality of the model becomes is not as good anymore, basically. So it's kind of like a hyperparameter to experiment with. Another method is related in the sense it's also about reducing KV cache size. It's another attention mechanism motivation. So here I'm just sketching a simple view of what happens in the attention mechanism. So we have an input and we have 3 weight matrices, and then we have the query key and value here that are computed. And in multi-head latent attention, which was introduced by one of the earlier DeepSeek architectures, what happens is that we have a compressed key and value that is shared. So we down project it with a weight, and then we up project it later during inference. And so this compressed key and value is the one that is shared in the KV cache. So instead of sharing the full keys and values, which are larger, we have the smaller intermediate representation. And similar to group query attention, it's reducing the KV cache size by a lot. Here again, 52 gigabytes of KV cache memory, and it goes down to about 13 gigabytes here. It depends, of course, on how big we make this compressed state. Again, it's a hyperparameter. We can have, for example, in this case, 1024, and then we have 13 gigabytes, or we can go down to 64, and then we only have 0.8 gigabytes of KV cache storage. So it's a hyperparameter. Again, we are we might affect the quality of the model, but based on the earlier DeepSeek papers, at the same compression rate, multi-head latent attention is usually preserving the model performance a little bit better than group query attention, for example. And yet also just an example, historically, people said, well, multi-head latent attention is more complicated to implement. So that's why some people don't do it. That's why they still stick with group query attention. But recently, for example, when the Zarva models came out, I think it was in March, they had actually both. They had one model with GQA and one model with multi-head latent attention. So you can't say, well, it was too complicated to implement, because they did it. But they deliberately chose to use GQA for the smaller model. And I suspect, I mean, I talked to some colleagues, I suspect it's MLA is a bit trickier to train. You have to do a bit more tuning, hyperparameter tuning, to get good performance. And there's a certain model size where GQA is basically performing similarly well, if not better. So it's not like universally true that MLA is always better. It's usually better, though, if you have larger models, like let's say in this case, 100 billion parameters or larger. But if you are working on smaller models, you don't have to use GQA. MLA, GQA might be just fine, for example. Unfortunately, the paper or report, the Sarum report, didn't have like an ablation study where they trained the same size with GQA and MLA, because that would also be very expensive to do a full run. But I think this is still some evidence, though, that there was a deliberate choice that for small models, maybe GQA is just fine. Another strategy would be modifying how much context in the past we can see or access. For example, on the left-hand side is another view on regular multi-head attention, or just one attention head. And so in particular, this is the attention weight matrix. And at each token position, the token can see itself, the one here, and everything that came in the past. So when we have a text, the model attends to past tokens. If we pick one token, for example, this 2, it can attend to 2 attends model the. So everything that comes before it, but nothing in the future. And that's like the standard autoregressive attention mechanism, the causal self-attention mask. And that is what is usually implemented in practice. Now, there is a technique called sliding window attention, where in sliding in window attention, we are restricting how much of the past the token can attend to. For example, here, it can still attend to itself, but only to a limited number of positions in the past. And the previous ones, they are not attended anymore. And in that case, we could technically evict those, the corresponding keys and values for those tokens from the KV cache. So we can save KV cache size by just restricting the window that the model or the attention can access. And so that's like another trick to shrink the KV cache size. So one model that just came out recently, for example, is Gemma 4. It came out last week. And this one, for example, uses both sliding window attention and group query attention. So it's like, it's a mix between both. And one could say, okay, if we use sliding window attention, it can only see a limited number of past tokens. But sometimes it's really important to have access to the whole sequence, because there might be really important information in the first position. And so in this case, that's why they did a 5-to-1 ratio, which means they have 5 sliding window layers, then 1 global layer, and then 5 sliding window layers, and so forth. So occasionally, every 6th layer is a global regular layer where it can access everything. So if there's important information, it's not lost. It can still be accessed, but it's not accessed at every layer, basically. It's just to make it more efficient that way. Oh, was the wrong button, sorry. And yeah, so here's the plot again. So a slightly different setup of an architecture. But if we have a setup here where multi-head attention takes 77 gigabytes of KV cache memory, if we add sliding window attention to the MHA, we get about 13.9 gigabytes. And we can combine it, like I said, with group query attention. So if we have regular group query attention with 19.3 gigabytes, and we add sliding window attention, we are down to 3.5. So it's like a huge reduction here. So it's actually quite useful, powerful method to reduce the KV cache size. Of course, there is more. There's also nowadays very popular the DeepSeek sparse attention. Some architectures adopted that one as well. It was proposed in DeepSeek version 3.2. And this is, I would say it's like a modified version of sliding window attention. So in sliding window attention, I mentioned we have a fixed bandwidth of past tokens we attend. For example, in the previous one, I chose 3 tokens in the past that we can attend. In practice, it's usually something like 1024. In DeepSeek sparse attention, it's the same idea. So we have a number of past tokens we attend, for example, 3, but they are learned. So for example, if we go to this here, to this row, you can see in this case, it attends this token, not this token, but this token. So the idea is the same. We restrict some tokens we can attend in the past, but instead of choosing them in a deterministic way, it's learned. It's it's still deterministic, but it's like learned during the training. What are the optimal positions? There's like a selection module, and the selection module is trained to select optimal positions, essentially. I mean, optimal in quotation marks, because it's like a local optimum, but it's like a way to select the past tokens a bit more smartly, and it's also like the same reduction of KV cache size. So I didn't include a plot here. And so DeepSeek version 3.2 proposed it, but it's nowadays also used by other models. For example, just last week, GLM 5.1 came out, and right now, as of this recording, GLM 5.1 is the flagship model, the best open weight model when it comes to coding and also, chatting and so forth. So if you go to the benchmarks right now, that's the strongest model, and it is also using both latent attention and sparse attention. Beyond just modified attention mechanisms, some architectures even completely replace attention in some layers. For example, there's Nemotron 3 Super or the other Nemotron 3 models. They replace some of the attention layers with Mamba 2 layers, which are kind of like a linear cost replacement for attention. They still, in the attention layers, use group query attention, but they replace some of them. And also that reduces the KV cache size because Mamba layers don't have keys and values. At the same time, they also have a modification of the MOE, the mixture of experts, using this latent idea, kind of like analogous to multi-head latent attention. But I know there's a lot of detail, and I don't want to like overwhelm you. I just wanted to mention there is also, another idea out there. And just to round it up, maybe the last idea here is TurboQuant, again, because it was such a popular model. I think it literally crashed the stock price of some of the memory chip suppliers. And so what TurboQuant does, it's kind of like what we just talked about the whole time. It's about reducing the KV cache size. So what they do is they quantize the KV cache. If we have a 16-bit precision representation of the keys and values, what it would do is it would compress this, for example, here 5 times compression to 2.5, 3.5. So it's like a reduced, a compressed state, again, to save KV cache size, to reduce the memory usage of LLMs. So like I mentioned, a lot of the focus right now is how can we make LLMs, I guess, cheaper to use, and how do we enable, like, given a certain compute budget, better, like more performance in terms of solving problems. And so starting with conventional LLMs, I mean, not too long ago, we just had like a regular chatbot, let's say GPT-4 or something like that. And then reasoning models came about, and reasoning models are more expensive to run. They are essentially beefed up LLMs where they are trained usually to generate more tokens, like the thinking trace. And that helps with coming up with more correct answers, or coming up with correct answers more often, working through more complex problems. But it's also more expensive to run because we have longer context, and hence the KV cache reduction motivation. And then I would say right now, 2026, the hottest topic is really running LLMs in an agent harness, so in agentic loop. There are many examples, for example, Claude Code, OpenAI Codex, OpenClaw. There are a lot of like applications that wrap like the LLM in a software harness that is kind of like helping preparing the context, what the LLM sees, but then post-processing it and giving it also access to tools. So just a few examples. I was also putting together a mini coding agent myself for education purposes to explain the ideas behind an agentic harness. But the idea is essentially that we still have the reasoning model or base LLM sitting in that harness, but then we have this loop where the model, let's say, inspects the repository, let's say the local Git repository, chooses a tool. If we say, I don't know, write us some unit tests, it would write the unit tests, create a new file, make sure the unit tests pass and so forth, and then observe the results basically and so forth. And that's our agentic loop where it kind of like almost, it looks like autonomously, but it is essentially just prompting it in a loop. And in that loop, we have different tools compared to just like a regular chat AI. So for example, we provide the repository context, we give it access to tools, file permissions, there's a memory file, a short-term cache to not recompute like basic things all the time that are not changing between each iteration and so forth. So it's like a lot of convenience features that are lacking in a chat UI. It's all like the kind of like the plumbing basically. So yeah, and I think that is like a big focus this year. How can we make that really good to get more out of the LLM? Instead of, let's say, just iterating on the LLM, there's also a lot of focus on making that better because it really gets more out of the LLM. So there are like different components to it, like I mentioned the live repo context, prompt cache, tools, and so forth. So if you're interested for educational purposes, I put together this little GitHub repository where I code this up in like a minimal Python code implementation. Yeah, and lastly, I promised you to share some getting started tips. And so I would say there are multiple levels when you start with LLMs. I mean, of course, I'm assuming you already used LLMs and you are familiar with the main idea behind LLMs, but I think still it can't hurt to really work from a like Python code perspective, work through the LLM from scratch, implement it one by one, because that really gives you like an unbiased way of how LLMs work. Because like we discussed earlier, like code doesn't lie. Like the code, if it's correct, if you have like an implementation where you know it's correct and you work or walk through it block by block, you're getting the real information. Like it's not like an abstract figure where things are missing. It's all there basically. So I think it's a great way to learn. And also like implementing a few LLMs and training algos from scratch is a good idea. Like I mentioned before, like I do with new architectures, just, building on an existing implementation, modifying it to get to that new architecture. I think it's also like a great learning experience to build some intuition. And then, if you want some starter projects, I have my LLMs from scratch repository, lots of bonus material, some starter architectures, also the whole build a large language model from scratch book, for example. And then reasoning from scratch is taking one of the pre-trained models, Qwen3, and implementing reinforcement learning and distillation and inference scaling methods on top. So more like the algorithms on the algorithm side. So I thought this might be also a good one where you have something more like the architecture and the algorithm to kind of learn how things work under the hood. And then from there, I would honestly consider wrapper libraries. So the previous ones I showed you, they are mainly for learning. But then if you have a real project, you want to run things on multiple GPUs, scale that up, and get some basic, let's say, projects done, I would turn to a library where it gives you access to more advanced, more optimized implementations where many people over many years optimized it and made it fast and convenient, basically. And so for that, I would really, just go to the classic Transformers library. It's pretty robust. It covers a lot of use cases. There's a lot of documentation out there. Torch Titan is also nice. It's like for pre-training mainly. It's more minimal. It's also a really good library. I think it might also be optimized a bit more towards pre-training because it doesn't try to do everything. And the TRL library is more like for the reinforcement learning, the post-training. But they're all like nice wrapper libraries that are making LLMs like convenient. But also you can choose any LLM that is essentially available on the Model Hub, given that your hardware supports that. Then going to the pro level here, that's a bit trickier. So that is really going to be expensive. So if you want to run these models, I would recommend, unless you are a company who is really determined to train your own LLM, I would only use those kind of for inspiration to see how did other people train existing LLMs. And then there's also still a lot to learn there. And you can replace, so if you go back to the beginner part, you can replace some of the code here with one of your from scratch implementations. For example, if you do the Gemma 3 270 million, you can drop it into the pro context here and just give it a try and see how it scales over different GPUs and how they set up the data set and so forth. And I think there's a really a lot to learn there. And so here I picked 4 libraries where they're all publicly available on GitHub. So the problem is, of course, most companies, they don't share their secret sauce. They don't share they share the weights, the model weights, but they don't share the training recipe. So it's all proprietary because that's like, the secret sauce at that company. There are some exceptions, though, that I'm listing here, where there are companies that are very transparent and they successfully trained reasonably big models that are competitive. And I think, so for here, I think it makes sense to really focus on those because there's an infinite number of code bases out there. But for those, we really know, well, they resulted in good models, so they must be working well, right? So there's almost 32 billion from LNAI. The Hugging Face, a small LM3, it's a really good model for its size. Of course, it's not going to be on the top of the leaderboard if you compare it to DeepSeek because it's a much smaller model, but it is a very powerful or capable model at that size. They mostly use the Hugging Face libraries like TRL, but they have a very good documentation too where they talk through this. Almost 3 in comparison, they have more like their own code base in PyTorch, pure PyTorch, not using, I don't think they use, if I recall correctly, Hugging Face tools. So it's like really different implementations, and they're very specific to their model, basically. They're not like a wrapper library. And then Intellect 3 is more like a post-training of an existing architecture. And then Nemotron 3, based on Megatron, that's a really good model right now. They also have a lot of detail in terms of code in their GitHub. And yeah, I hope you found this useful as like a brief whirlwind tour from what it means in terms of coding LLMs in Python, what we can learn when we code through an architecture from scratch, and to tools. What tools are out there? What are good resources to start with? And just a side note, shameless plug here. My new book, Build a Reasoning Model from Scratch, is out. It's not out yet. It's in production, but the last chapter I finished that, so it's all available on the Manning website as the pre-layout. It's not the final layout. There will be nice syntax colors and everything, but it's already available for pre-order on Amazon and Manning, the whole 528 pages. And yeah, it was like a really, I guess, my most ambitious project. I worked on it for more than a half years. Lots of code, lots of figures, lots of experiments, hundreds of experiments. And I hope with that, it's like a good learning resource to understand how inference scaling works, reinforcement learning, and distillation. And with that, thanks for listening. I hope you found this useful, and until next time.